All right, class. Today I'm going to talk about TLC. Every time I'm teaching this in person and I ask my class, what do you think TLC stands for? Everyone says tender, love, and caring. That is so not happening in chemistry. There is no loving and caring in chemistry. TLC stands for thin layer chromatography. Now, before we talk about TLC and what it is and how we use it, I want to go over why TLC is important. TLC is important because it's going to help us to assess product purity. So once you make your product, you can use TLC to figure out if it's pure or no. You can use TLC to monitor your reaction to see if your reaction is done or not. You can do that to support identity, of your product. But I said support the identity. That's really key. It will just confirm it. You can figure out what you have based on TLC. And the last thing is TLC can help you to figure out how many compounds you have in a mixture. So these are some of the things that TLC, thin layer chromatography, can help you do. If you have a product, to figure out how pure it is, to monitor your reactions, if the reaction is done, to support the identity, to basically confirm the identity of your product, and then to figure out how many compounds you have in a mixture. All right, so far so good. Now let's go over what TLC looks like. So this one, what I drew right here, this is a TLC plate. And TLC has two phases. So here is a TLC plate. And a TLC plate is a sheet of glass or metal or plastic and is coated with a thin layer of silica. And that is my stationary phase. Okay, so here is a TLC plate. I'm going to call this a stationary phase. So it's usually a piece of glass or metal or plastic and is coated with a thin layer of silica. And that is my stationary phase. And you guys know what silica is made of? Silica is SiO2. That's like a fun fact for today. So far so good. Okay, so that is one phase. That's the stationary phase. Now, when you do experiment, what you are going to do, you have to put your sample on the TLC plate. Okay, so the way we do this, pay attention to this part, about 1 centimeter from the bottom. Okay, about 1 centimeter from the bottom, you usually draw a very faint line with a pencil, not a mechanical pencil, with a regular pencil. So about 1 centimeter from the bottom, you're going to draw a very faint line on the TLC plate. Okay? Then and very gentle. You're going to make this line very, very gentle. Don't go too crazy on it. And then what you're going to do, you are going to spot your samples on this line. And when you spot your sample, you should definitely leave some space in between. Okay? So you're going to spot your samples on here. Again, we're going to go over all this in detail again. Just want to give you an overall what a TLC is. Okay. So again, you measure about 1 centimeter from the bottom and you are going to gently, very gently draw a line. Don't press too hard on this silica plate, on this TLC plate, and don't use a mechanical pencil. And then you are going to, after you do that, you're going to spot, I don't know why I keep doing that, you're going to spot your sample on this line and you're going to leave room between the samples. So far so good? Okay. Now what are we going to do? Now we're going to take our TLC plates and put it in our developing chamber. So I'm going to have this jar, okay? And on the bottom, we're going to add solvent, okay? So here, we're going to add solvent. Now, this is going to be my mobile phase. Okay? Now, what I'm going to do, you're going to take the TLC plate and you are going to put the TLC plate in the jar that has a solvent, okay? Now, this is going to be our mobile phase, and I'm going to talk about why that is. Now, here is a key to kind of think about this. I took this TLC plate that we had and I put it here, right? This is TLC plate from the last page. And I put it here. And there's a solvent in this container already. So I have a jar with a solvent and I add my TLC plate to it. You follow that? I'll repeat it again. I'm going to have a jar with the solvent and I'm going to add a TLC plate to it. Now, look at my drawing. I know my drawings are usually questionable, but not this time. If you look at this, I have this line that you have your samples on is above the solvent. That's really, really key. This has to be above the solvent. Otherwise, the TLC is not going to be very accurate and it's not going to work. So this line has to be above the solvent line. Okay? Now what happens? What happens is when you put your TLC jar in this, your TLC plate in this jar that has solvent, the solvent slowly is going to move up the plate, and as it's moving up the plate is going to carry these compounds with it up the plate. So let's take a step back. So you're going to have this jar with the solvent in it. You're going to put your TLC plate in there. Once you put your TLC plate in there and it has your compounds on there, the solvent is going to slowly move up the plate and then is going to carry these compounds up the plate with itself. Okay? Now, hold on a second. What happened to gravity? Why is this going up against gravity? If you remember in Chem 1A, capillary action, right? Is moving up the plate using capillary action. Then what are you going to do? So you're going to sit there and you're going to watch this solvent go up the plate. And as this solvent goes up the plate, is going to take all these compounds with it, you're going to see that the plate is going to get wet. So as the solvent keeps going up the plate, you're going to see that this TLC plate is going to get wet. You're just going to sit there and you're going to watch this happening. And then, when the solvent is about 0.5 centimeter to the top, you're going to remove the TLC plate. Okay? So again, the solvent, as it's going up, is going to make this TLC plate to look wet, right? And you're going to watch this happen. You're going to watch this solvent keep going up. When it's about 0.5 centimeter before it reaches the top, you are going to remove the TLC plate. Now, I want to draw it here. So I'm going to remove the TLC plate. So I just remove the TLC plate from the chamber. And remember, you had this line and you had your compounds in there. All right, now here is what you're going to do. When you remove the TLC plate from your jar, remember, when it was about 0.5 centimeter to the top, you took the TLC plate out. Now, immediately, you are going to mark the solvent front. So you immediately, with a pencil, gently, you're going to mark the solvent front. Now, what's the solvent front? That's where the solvent ended. Because you took it out, you didn't let it go all the way to the top. So that's where this solvent ends. Then what you're going to do, you're going to let this dry. What you're looking for, you should see spots on the TLC plate, because remember, as the solvent went up, it took these compounds with it, right? As the solvent went up the plate, it took the compounds with it. So what you should see spots on the plate. Let it dry. If you still don't see any spots, then place it under the UV lamp and see if you can see the spots. Now, what should you expect? Again, you should see spots. Let's see. You should see spots. Like this maybe. For example, you should be able to see spots on the TLC plate. Now, if the spots are too large or they're too concentrated, you might see streaks instead of nicely dot spot. If you see streaks, that means the spots were too. By streaks, I mean you see like a huge line here instead of dots. If you see that, for example, you will see something like this. That's a streak. That's not good. What you want to see spots. If you see something like this, what that means is the spot was too large or it was too concentrated. So you would have to do it again. So far, so good. Okay, beautiful. I want to give you a scenario right now to make sure you really understand the concept of TLC and why we use it. Let's say I have a mixture, I have a compound, right? Let's say I have a compound, my product. I just did a reaction and I got my product and I'm really, really excited about this product. What I'm going to take a TLC plate. I'm going to spot my product on a TLC plate. And then I'm going to put it in a developing chamber. I'm going to add solvent to it. I'm going to watch the solvent go up the plate. And then when they went about 0.5 to the top, I'm going to remove it. I'm going to let it dry. And then I'm going to look at my TLC plate. Let's say I look at my TLC plate and this is what I see. What does this mean? What does this mean? Good TLC, bad TLC, good product, bad product, what do you think? Remember, one of the things that TLC can help you assess is the purity of your compound. So I put my product, my compound on a TLC plate. What I ended up seeing 3 dots instead of just 1 dot for my product. What does that mean? Why do I have 2 extra dots? That means impurity. That means this has impurity because that means this was a mixture. This was a mixture of different compounds. So when it went up the plate, then the TLC was able to separate those and I see a dot for each of those compounds. So probably 1 is my compound and the other 2 is the impurity. Okay? So what that means is the rate that the compounds go up the plate is different. This is why if my product was a mixture and it was not pure, I would get more than 1 dot. Because the other products, the other compounds that were mixed with my product, they are going to travel up the plate at a different rate. And that's how I can see if my compound was pure or not. I'm going to repeat this one more time because this is the first time you're hearing about TLC. So I have my product. I'm hoping it's pure. If my product was pure, after doing a TLC, I would just get 1 dot. But I got 3 dots. That means my product was not pure. And this was a mixture and other things were in here. So I have 2 impurities in there. I have 2 impurities in there. Okay, nice job so far. When we talk about TLC, RF value is one of the things we look for. what's the RF value? What the RF value is the distance traveled by your compound over distance traveled by the solvent front. This is what the solvent front really matters. So what does this mean? Let me draw a TLC plate for you again. Hopefully you're pretty good at drawing the TLC plate. So let's say I have a TLC plate, okay? I have this line and I'm gonna put one compound in there. I'm gonna put it in a jar, put it in a development chamber, and it's gonna have solvent. It's gonna keep going up, and then when the solvent is about 0.5 centimeter to the top, I'm gonna take it out and I'm going to mark the solvent front. Remember, this was a solvent front. So the plate is gonna get wet. You're gonna see it. It gets wet, and then just keep going up. You're gonna see it going up. And it's about 0.5 centimeter to the top. I'm gonna take it out. Again, it doesn't have to be exactly that. You can eyeball it. I'll trust you guys. You can do this. Now, I'm gonna let it dry. And then when I let it dry, I'm gonna see one dot. First of all, when I see only one dot, I go, yay. That means my product is pretty pure. So that's a good thing. See one dot is good. That's what I wanted to see. Now, then what we're going to do, we're going to figure out the RF value for this dot. To figure out the RF value, circle the center of this dot. Okay? It's not very center, but you know. Let me try one more time. So take the center of this dot. From the center to over here, which was the base, you are going to measure that. And I'm going to call that B. Okay? So that's the distance traveled by the compound over the distance from here, from the solvent front to the base. I'm going to call that A. That's the distance traveled by the solvent front. B divided by A is going to give me an RF value. What does RF stands for? Retention factor. Sounds kind of cool. Retention factor. So you can measure the RF value. So now you have a value to compare things. Okay? Now, let's say I have two compounds and they both have 0.2 RF value. Does that mean they're the same compound? They may or may not be the same compound. Usually the best way to see if two things are the same is to run it side by side on the same plate, right? That's because if every plate if you use a different plate for a different compound, you're changing so many variables. The best thing to do is run things side by side on the same plate and then compare the RF value. Okay, so far so good. Now let's summarize what we talked about. So the TLC, thin layer chromatography, it has two phases. The mobile phase, which is the solvent, the stationary phase, which is the silica plate, right? So they said TLC plate, the silica plate, that's my stationary phase. What you're gonna do, you're gonna spot your compounds, and then what's gonna happen, your compounds are going to move up the TLC plate, and different compounds are gonna go up the TLC plate at different rates. And based on that, we can measure an RF value to compare things. Also, if you do one compound, you spot one compound here, and if you go up and you see several spots, that means that compound is not pure. Now here I have a TLC plate. I have three compounds I spotted on this TLC plate. A is a benzene ring, B is an alcohol, and C is a carboxylic acid. And these three are pure. I know they're pure. I'm going to put it in a developing chamber, and they're going to go up with the TLC, with the solvent, and about 0.5 from the top. I'm going to mark the solvent front. Here's what I want you to do. Predict where these 3 dots are going to end up relative to each other. To know that, you have to know what's the theory behind these compounds going up the plate. So I'm going to tell you about it, then I'm going to ask you the same question again. So pay attention. What happens is, the way they go up the plate is based on the polarity. Is purely based on the polarity. Brings back Chem 1A stuff. The silica plate is fairly polar. The silica plate is fairly polar. Now, I need you to remember this from Chem 1A, especially if you had me. I had you repeat this in class. Like dissolves like. So if this silica plate is polar, the silica is going to like compounds and interact with compounds who are also polar. And they're going to stick together. Now, if you have a non-polar compound, the silica is not going to be too crazy about. Okay? So, I'll repeat this again. Silica plate, the TLC plate, is fairly polar. So it's going to interact strongly with polar compound. Now, if it's going to interact strongly with polar compound, the polar compound are going to like this silica plate. They're going to hang out with each other. So they're not going to move really fast up the plate. It's kind of, let's say, if I run into my friend and we're walking together, I'm enjoying my friend, I'm talking to my friend, we're hanging out, we're not going to walk fast, right? Versus if I see one of you guys on campus, I'm just going to walk really fast. Just kidding. So if I have a non-polar solvent, the non-polar is not going to like the polar plate so much. So it's not going to hold on tightly. It's going to move up really, really fast. So far, so good? Okay. So let's repeat this again. So silica plate, TLC plate is polar. If I have a polar compound in there, the polar compound is going to like the TLC plate. So it's going to interact with this TLC plate. So it's not going to move up very fast. If I put a non-polar compound here, it's not going to hold on tightly because non-polar and polar, they do not like each other, right? So it's going to move up pretty rapidly up the plate. Now, based on what we just talked about, I want you to predict these dots, basically relative to each other. Where do you think they are going to end up? Relative to each other, where do you think they're going to end up? Pause my video, do this, and then we're going to do this together. So, if I look at this one right here is really, really non-polar. Do you guys agree? And this one, if I rank to polarity, this is super polar. I'm going to put super polar. And this one is polar. So the non-polar, we said, is not going to like the polar silica. They don't like each other. They don't mix. It's just going to run really fast up the plate. So I expect this one to have a high RF value. The alcohol, yeah, fairly polar. It's going to hang out a little bit with the TLC plate. Carboxylic acid, oh, that is really, really polar. Acetic acid is going to hang out so much. They're going to talk so much that they're going to forget to go up the plate. Yeah? All right. I'm going to repeat the concept one more time. The TLC plate, silica, is polar. So if I have a polar compound on there, the polar compound is going to interact with the polar TLC plate. They're going to interact strongly, so it's not going to move up the plate really fast, as you can see over here. On the other hand, if I have a non-polar compound, the non-polar compound does not lock the polar TLC plate. It's going to move up pretty fast up the plate and is going to have a high RF value. So this is how you can also predict, before you put it on there, what kind of RF value you predict. All right, nice job.